For this last lecture, it may be a little bit longer than 15-20 minutes. I'm going to go over some of the other endocrine glands. Beginning here with the thyroid gland, we're going to look at the thyroid gland and the adrenal gland most specifically, but make sure you study the other glands and know again their anatomy and where they're located, the hormones they produce, the target organs, and what the effects of those hormones are. So if we take a look here at the thyroid gland, recall that this is located in the throat. So it's right in this area here in the throat. It's a butterfly-shaped gland. This is the larynx or voice box. This is the thyroid cartilage. You may know it as the Adam's apple. And so the thyroid gland is just below that, and it overlies the windpipe, also known as the trachea, or you may hear it called trachea. That's more of a European pronunciation. The two lobes of the thyroid gland are joined together by a structure called an isthmus. Now, the thyroid gland is a true endocrine gland, and it is the only gland in the body that stores hormones. So it stores about 3 to 4 months worth of thyroid hormone. So present within the gland, if we take a look at the histology, we have these little pockets that are filled with a substance called colloid. Colloid. It's also known as thyroglobulin. It's a gelatinous type fluid that is the precursor to thyroid hormone. The substances that make up colloid, they have to bind iodine in order to complete the production of thyroid hormones. The cells around the outside of each of these little sacs called follicles. Okay, so that's a follicle. That word means little sac. So let's take an enlarged diagrammatic view. These cells around the outside that form the wall of a follicle, which is going to be shaped like a little ball like this. And this is a slice through that ball so we can see the cells. These are called follicular cells, and they produce the thyroglobulin and the thyroid hormone. The other cells that are located in between follicles, known as parafollicular cells, they produce a hormone called calcitonin that functions in calcium maintenance of the blood, and it keeps the calcium from getting too high. We have two types of thyroid hormone, T4 known as thyroxine and T3 triiodothyronine. The most active form is the T3. However, more T4 is secreted. When the T4 arrives at the target cells, one of the iodines is removed. That's what the 3 and 4 means. 3 on the T3 and 4 on the T4, so that we have the active T3 in place. I will let you read the slides related to the function of the thyroid gland, but it is known as our major metabolic hormone. We need it for all the metabolic activities that occur within the cells. Growth hormone, thyroid hormone is necessary for growth hormone to work properly. Let's take a look at how thyroid hormone is synthesized. So here we have a follicle and the follicular cells, and this is a capillary. It's important to note that all of our endocrine glands are very well vascularized because of the amount of transportation of substances into and out of our glands. So here we enlarge this view. Here's the capillary. Here's a follicle cell, and this is the lumen of the follicle. I want you to recall that the word lumen is the open space inside a hollow structure in the body. Sorry, my nose is itching. So from the blood transported into and across the follicle cell are all the substances that are needed to synthesize the colloid In addition to that, iodine has to be removed from the blood and transported also across the cell membrane. The substances that are brought into the cell then produce the thyroglobulin, which is transported and stored within the lumen of the follicle. The iodine is carried across and bound to the thyroglobulin, producing T3 and T4. Prior to it being T3 and T4, it's T1 and T2. So T3 has 3 iodines. These are the green dots. And T4 has 4 iodines. The T3 and T4 then again must be transported through the cell and released into circulation to go to the target organ, target tissues, which are all the cells of the body. Be sure for each of the different hormones and endocrine glands that you study that you know some of the dysfunction that can occur. For example, for most of them, it's either going to be an overproduction, which would be hyper, or an underproduction, which would be hypo. So for an example here for thyroid, a hypothyroidism in adults is called myxedema. That's a diminished amount of thyroid hormone being produced for various reasons. And then in hypoproduction in infants and newborn children is called cretinism. And of course, the child will not develop properly. So they treat any hypothyroidism type disease is treated with hormone therapy. Another hypothyroid disease that is an autoimmune disease is known as Hashimoto's. The immune system attacks and destroys hormone producing cells of the thyroid, resulting in diminished thyroid hormone. So the symptoms would be similar to myxedema, and it's also treated with T4. And they may even use immune suppressing drugs. Graves' disease is an autoimmune hyperthyroidism. This is a very unusual type of autoimmune disease. When the immune cells attack the thyroid gland in this situation, they begin to produce continuously stimulate the production of TSH, or they stimulate the, let me try that one more time. They mimic the function of thyroid stimulating hormone, causing the thyroid gland to keep producing thyroid hormones. And that then results in an increase in thyroid hormone, and we get the hyperthyroid symptom. In any situation of a thyroid gland imbalance, it can affect a person's moods. They can become very moody, hyper, depressed, various types of situations, because the diminished or increased thyroid hormone, of course, is going to affect brain cells. So it's important for someone developing these symptoms to have treatment immediately and see a specialist or see a doctor, medical doctor. On the posterior aspect, this would be a thyroid gland. We remove and look at the back of the thyroid gland, the posterior, and embedded within the thyroid gland are these small other glands called parathyroid glands. They produce the hormone PTH, and PTH, that's parathyroid hormone. This is a very important hormone in regulating blood calcium. Parathyroid or PTH hormone is stimulated to be released when calcium blood levels drop below a certain amount. And PTH stimulates osteoclasts in the bone to release calcium to the blood. They stimulate the kidneys to hold calcium. They put calcium back in the blood. The kidneys will also take the substance produced in our skin when exposed to sunlight, vitamin D, and they convert it to its active form, which is D3. And this is needed to increase the absorption of calcium from the food in the gut. So the action of PTH is threefold. When the blood levels of calcium reach the normal level, then it'll feed back to the parathyroid glands, and PTH production will then diminish. Let's move down to these two triangular or pyramidal shaped glands that sit on top of the kidneys. These are called the adrenal glands, also known as suprarenal. That means added to the renals. That's another word for the urinary system or the kidneys. These glands, the adrenal glands are two glands in one, like the pituitary. An outer part, the adrenal cortex, is true endocrine tissue. The middle part, adrenal medulla, is actually nervous tissue that is under the control of the sympathetic nervous system. Let's take a look first at the adrenal cortex. The adrenal cortex consists of three distinct layers of cells that produce three different types of hormones. All of the adrenal cortical hormones are steroid hormones, and they function in controlling the amount of salt that's reabsorbed into the blood, thus helping control our blood pressure. They produce a steroid hormone known as cortisol that is needed in our long-term stress response. The deepest layer, known as zona reticularis, produces weaker sex hormones. So let's take a look again, and we're going to look at each layer. So you need to be sure that you know the name of each layer, the hormone produced, and the action of that hormone. So the outer part of the adrenal gland is encapsulated within a fibrous type capsule. Just deep to that, and these layers go all the way around the gland. So just deep to that, the most superficial layer called zona glomerulosa. This is the layer that produces what are known as the mineral corticoids. The next layer, long lines of cells stacked on top of each other that look like fascicles. That's called zona fasciculata. This produces the glucocorticoids. And then the layer that produces the gonatocorticoids is called zona reticularis. And then finally we get to the middle, which is the adrenal medulla. Now the mineral corticoids I'm going to go to this picture. The mineral corticoids produce a very important, or consist of a very important hormone known as aldosterone. Aldosterone is really important in controlling our blood pressure and blood concentration. When aldosterone is secreted, it will cause at the kidneys, in the kidney tubules, as the fluid is being adjusted and formed into urine, it will cause the kidneys to hold sodium back into the blood. When the sodium goes back into the blood, because the blood then becomes more concentrated, water's going to follow that sodium in and thus increase the blood volume, decrease the concentration of the blood plasma, and it's going to cause a rise in blood pressure. When potassium levels are too high within the blood, aldosterone will stimulate excretion of potassium in the urine. The glucocorticoids include the most important of those glucocorticoids, are major stress hormone known as cortisol. You guys have probably heard of cortisol before. We have to have cortisol being produced daily in order for us to function throughout the day. So cortisol is secreted on what's known as a diurnal cycle. Diurnal cycle. D-I-U-R-N-A-L. That means over a pattern like a sine wave. So on a normal day, we're going to have cortisol secretion like that. On stressful times, we're going to secrete more, and it can stay higher for longer periods of time. Cortisol reaches its peak early in the morning Okay. And then this is how it's supposed to be. And then when we go to bed and sleep at night, it's going to be lower in the PM. Okay. In all of these situations, for any of the adrenal cortex hormones to be secreted, they are stimulated by ACTH, secreted from where? Ha 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 ha. Do you remember where ACTH comes from? From the anterior pituitary, under the control of CRH from hypothalamus. Remember that? Some of the things that cortisol does is it causes the conversion of substances to release more sugar into the blood, because these are going to be times when we need more energy. So that's one of the major roles of cortisol. Pathology or problem with the adrenal gland. Cushing's disease is too many adrenal cortex hormones, while Addison's disease Addison's is considered to be an autoimmune type disease, but this would be hyposecretion. Addison's disease can kill someone relatively quickly, and so it has to be treated with corticosteroids. And then our gonatocorticoids are hormones called androgens. They are primarily male sex hormone testosterone, and they're converted to stronger forms. These tend to be elevated at the onset of puberty. Of course, we can have a secretion of these in a stress response, because that action of testosterone also is like getting epinephrine, norepinephrine. The adrenal medulla is the middle part of the adrenal gland. It's called a neuroendocrine gland because it's mostly neuro, whereas the adrenal cortex, like the anterior pituitary, is an adenoendocrine gland. The two hormones that are secreted from the adrenal medulla are epinephrine and norepinephrine, and these are our short-term stress response. So let's take a look at this next slide, and we want to see what actually is happening with the stress response. When we experience a stressful event, say you get frightened, you're going to your car at night and you see some scary things happening and you are frightened, that triggers the fight or flight stress response that's mediated through the nervous system called the sympathetic response. In addition to the sympathetic nervous system innervating the heart and lungs and blood vessels, it's also going to release epinephrine and norepinephrine into circulation so that it can have a widespread effect throughout the body. The purpose of that stress response is to make you ready to act. So we're going to get things like an increased heart rate. We're going to get increased blood pressure. We're going to get vasoconstriction, which is the vessels constrict in order to help raise the blood pressure. We're going to get a conversion of glycogen into glucose and get released to circulation. We're going to have a dilation of bronchioles and increased blood flow through the heart to the heart and skeletal muscle, and an increase in our metabolic rate. And that's going to take place instantly. At the same time that the sympathetic nervous system is being activated via the hypothalamus through the limbic system, hypothalamus is also going to secrete CRH, corticotropic releasing hormone, to the anterior pituitary. It will then release ACTH to the adrenal cortex, causing an increase in adrenocortical hormones. So they're going to have a longer term effect because they're going to cause the kidneys, again, remember aldosterone, increase reabsorption to the blood of sodium, which will cause water to come in back into circulation, increasing the blood volume and blood pressure, more conversion of other substances into sugar to release to the blood to increase the blood sugar level. And over the long term, we can have a suppressed immune functioning if this continues. So that's why when you are in school for a semester and your stress level is high from school and work and family and all the responsibilities that you have, when that one last stressor of schoolwork ends at the end of the semester, in a day or two, you might come down with a cold or get sick because of that increased amount of steroid hormones from the adrenal cortex have suppressed the immune system and its ability to fight off germs, in case you ever wondered. Let's move back next to the pineal gland. The pineal gland is very easy to understand. It's in the epithalamus of the diencephalon in the brain. But I wanted to point out to you that the pineal gland, in producing melatonin, this is our sleep regulating hormone, it also secretes on a diurnal cycle. But its diurnal cycle is opposite of cortisol. So its highest level is at the PM at night and lowest during the day. And one of the things that stimulates the production of melatonin is our exposure to light, particularly sunlight and blue light. That's why they say try to turn off all your screens an hour before bed, because that exposure to light can inhibit the production of melatonin, that light that comes from the screens. Sunlight, however, stimulates the pineal gland to begin to produce the melatonin in the day. It gives us a normal circadian rhythm. In fact, fibers of the optic nerve do pass right through the pineal gland. So our normal exposure during the day to daylight or sunlight, and then diminished in the evening, keeps the pineal gland on normal function. So that's your PSA for today. The pancreas. The pancreas is a very exciting organ. It's located just posterior to the stomach in the abdomen, and it's nestled right in here in the small intestine, in the first part of the small intestine called the duodenum. We're going to be looking at the pancreas again on digestive system because it has a dual role. It has an exocrine function, and an endocrine function. The exocrine function is the production of the digestive enzymes that we need to break down all the food that comes into our intestines. So exocrine, it's going to secrete into the duct and go into the small intestine. What we're going to be looking at is the endocrine function now. The endocrine function is the pancreas's ability to control our blood sugar levels. So we have the two hormones that are produced that control and maintain our blood sugar in the normal range that we need in order to produce energy. So dispersed throughout the acinar cells of the pancreas are little islands of cells. Let me go back here for a moment. Little islands of cells called pancreatic islets, or islet of Langerhans. That word, I-S-L-E-T, is pronounced islet, like E-Y-E-L-E-T. That's how it would be pronounced, islet. Those little islets contain two types of cells, alpha cells and beta cells. The alpha cells produce glucagon. Alpha cells produce glucagon. Beta cells produce insulin. Glucagon increases blood sugar. And on the next slide, you can go over the different functions of glucagon and how it increases blood sugar level, while insulin decreases blood sugar. So we call glucagon a hyperglycemic chemical or hormone because it's going to raise blood sugar. And insulin is a hypoglycemic because it's going to lower blood sugar. The important part is we have to have the right amount of blood sugar to keep all of our cells making ATP energy. This is why we need oxygen. And when we add oxygen to C6H12O6, sorry, I don't write good with my mouse. O6, that's glucose. These two together, I think it's 6 of those, gives us ATP. We're going to learn more about this later on in the semester. And we get water and CO2 with that. And CO2, okay? Oh, thanks for putting up with my writing there. Yeah. It's so much easier to write it on a classroom whiteboard. Okay, so what's really important about this in maintaining our blood glucose levels is that our nervous system uses glucose exclusively to produce energy, our brain and nerves. And our nervous tissue is extremely metabolic. It's always very busy, so it needs a lot of ATP energy all the time. It's producing all kinds of neurotransmitters. It has to transport all those neurotransmitters along the cell membrane or inside the cells to the axon terminals. You can review all that stuff at the chapters 12 through 15 in the textbook if you want to review the nervous system function. It doesn't really talk much about the ATP energy needed, but any transport from a nerve cell body down to the axon terminals at a synapse is going to need ATP energy. And remember, some of those axons are very long, several feet long. That's a long way that the ATP energy has to be transported. It doesn't just float there. And we particularly need glucose for the brain. Ever notice when you get hungry that you get crabby and shaky? Yes. So it's really important to release that glucose to the blood for the brain. Some of our other body cells can burn fat for energy. They convert fat into substances that can go into the cycle to produce the ATP energy. But the brain, except in the case of starvation, the brain needs glucose energy. Thank you. So these are what glucagon versus insulin does. And then recall that our regulation of the pancreatic hormones is going to be a negative feedback mechanism, and it is a humoral response that occurs by the rise and fall of the blood sugar level. I want to talk about diabetes. So diabetes, blood sugar type diabetes is a problem with either the secretion or the activity of insulin. There are two main types and a third type that's not the main type. The two main types of diabetes are type 1. This is an autoimmune disease where the immune system selectively destroys the beta cells which produce insulin. This has been known as juvenile diabetes or insulin-dependent diabetes. It's important that you remember this is autoimmune. And they don't really call it juvenile anymore because adults have developed type 1 diabetes. Type 2 diabetes is probably the one you've heard the most about. The person makes the insulin, but either the insulin's not working properly or the cells of the person's body are not responding to process the glucose. So there are medications, not necessarily insulin is given to the patient, but there's various medications to help control type 2 diabetes, and this can also be reversed by diet and exercise. Gestational diabetes is like type 2, but it only occurs during pregnancy. The three cardinal signs, meaning the major signs of diabetes, are polyuria, polydipsia, and polyphagia. Our last endocrine glands, which are combination endocrine gland and other functions are the gonads, which are testes for male and ovaries for female. And testosterone is produced by the testes, while estrogen and progesterone are produced by the ovaries. These control puberty. They increase in puberty, so they're responsible for secondary sex characteristics. They are needed in order to produce gametes, sperm for male, ova for female, and they are needed to maintain the health of the sex organs, and they also affect other functions in males and females. Then we'll look at this more at the end of the semester when we study reproductive system. So I thank you so much for listening to this lecture, and I wish you the best in learning about the endocrine system.